Okay, thank you, Professor Kim, for the introduction. Good afternoon, everyone. Once again, it's my great honor to receive this award and have the opportunity to present our work here. The title of my talk is Quantum Control of Microscopic Systems and Precision Measurement. I'm Yong-Chun from Tsinghua University. This is the outline of my talk. First, I will give a brief introduction, and then I will introduce progresses of our recent work. So there are mainly two parts. The first part is about the quantum state calculation based on information control. So this part is mainly theoretical work. And the second part is the precision measurement of magnetic field. So this part is about experimental progresses. So as we know, quantum mechanics has been established for more than 100 years, but still there are a lot of things to be done because actually we haven't maybe used of all the powers of quantum technology. So in recent years, people have, scientists have made efforts in quantum control of atoms and photons. For example, in 2012, the Nobel Prize is awarded to Professor Haroshi and Weinand for their groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. And the Nobel Prize in 2022 awarded to Professor Aspect, Clauser, and Zillinger for their experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. So nowadays we can make use of quantum technology to find applications in quantum information and also quantum precision measurement. But we can find that they are focused on only a few number of particles. So what about extend from macroscopic to from microscopic to macroscopic? So what I mean is we can extend from small particle number to large particle number. So this is the main research field of my work. So I'm working on this quantum control of macroscopic systems. So of course there are a lot of macroscopic systems. And we are focusing on these two kinds of systems. First one is atomic number with a lot of atoms. For example, the atom number can be up to 10 to the 10 to sorry, how can I go back? Okay, yeah. 10 to the 12 and 10 to the 14. So for this case, the atoms have the spins. It's actually atomic number with a lot of spins. We can use light to interact with these atoms. The other system is a cavity optomechanical system. It studies the interaction between light and the mechanical resonator. So for this kind of mechanical resonator, it can be quite macroscopic. It can contain even more atoms. So why do we study this kind of macroscopic systems? Because we can use this kind of system to study the quantum classical boundary. That is, explore the difference, the boundary between the quantum theory and the classical theory. And the second thing is that we can use this kind of systems to realize the quantum precision measurement of physical qualities. So because when we have more atoms, it means that the signal will be strongly enhanced. So we prefer systems with a lot of particles. So the first part of my research progress is about quantum state calculation based on interaction control. So we are trying to prepare quantum states in this kind of system with a lot of atom numbers. This is a typical experimental system with thermoatomic examples. This is an actual device. The size is about 1 cubic centimeter. And inside this glass cell, there are a lot of alkaline atoms. Typically, we use rubidium, and also we can use potassium or cerium. So this kind of system has a lot of atoms, and it can have long coherence time for the spin, and it can be easily initialized and read out by light field. So for this kind of system, we call it a collective spin. For a single spin, we can describe it using two-level use the Pauli matrix, and the Pauli matrix can also describe the two-level systems. So we can have this block sphere. For these multiple two-level atoms, we need to use the collective spin operator. So this is just the sum of all the spin operators for the individual atoms. And then we can find this collective spin operator is just an angular momentum, and it has this commutation relation for different components. They do not commute. So there is an uncertainty relation here. This means that the three components cannot be determined simultaneously. So there will be a quantum noise. If we look at the state of this kind of system, we can find that one important state is coherent spin state. It means that multiple independent covalent atoms, they have no correlations, no interactions. Now in this case, we can obtain the expression of this coherent spin state. It's just the direct product of n atoms. So we can obtain that there is uncertainty in the spin component here. This is proportional to the square root n. And we can use extended Bloch sphere to describe it. So for this Bloch sphere, we can find that the spin projection noise for this coherent spin state is uncertainty circle on the sphere. So there's another kind of state called the squeezed spin state. So this is a comparison. This is coherent state. This is a squeezed state. It corresponds to an uncertainty ellipse on the Bloch sphere. According to the Heisenberg uncertainty relation, it means that along some direction, the fluctuations, the spin projection noise can be smaller than the coherent state case, and along the other direction, the spin fluctuation becomes larger. Then we can define a squeezing parameter to describe the squeezing degree. So if this parameter is smaller than 1, it means that it has a smaller noise than a coherent state case. So it will be better. So for these two different kinds of states, we have different quantum limits. For example, if we have a coherent spin state, we can find the final limit for this system is a so-called standard quantum limit. So it is proportional to 1 over square root n. N is a particular number. And for a squeezed state, we can get a better result, better precision. And finally, it will be restricted by this Heisenberg limit. This is proportional to 1 over n. How to generalize such kind of squeezed state? Also, we can say spin squeezing. So the most common method is using nonlinear interactions. So there are two toy models to realize this kind of state preparation. So the first is one-axis twisting, OAT. So the Hamiltonian is like this, is proportional to GZ square. And the second interaction is two-axis twisting, TAT. So the Hamiltonian is like this, GZ square minus dy square. So we can have a direct view on this sphere. So we start from a coherent state. Then, according to this one-axis twisting interaction, we can find the evolution speed on the Bloch field is proportional to chi Gz. It means that when Gz is larger, then evolution speed will be larger. So it means that if the state is far away from the center, it will evolve much faster. And then finally, it will evolve from this circle into this ellipse. And for this two-axis twisting, TAT, things are similar, but they are two twisting axes. So actually the squeezing will be better. If we compare these two kinds of models, we can find that for OAT, the disadvantage is that actually the squeezing is lower according to this blue curve. But the advantage is that it will be easier to implement in experiments because, for example, in Bose-Einstein condensates and in cavity QED system with light atom interaction, we can realize effective one-axis twisting interaction. For this TAT, we can find that the squeezing can be higher and it can approach the Heisenberg limit 1/n. But the difficulty is that it's hard to implement in real experiments because actually we cannot find a direct system realizing this kind of interaction. So we have an idea to dynamic synthesize the interaction. So the basic idea is to control the evolution dynamics by applying rotational pulses. So this rotation is along the Bloch field. So if the original interaction is OAT, then we apply this rotational pulses. If we look at this time average the effective interaction, we can find that it can be effective TAT. So using this kind of method, originally non-existent interactions can be synthesized. So we call it dynamic synthesis of interaction. So we have this idea very long time ago, almost 15 years ago, I started to explore this idea, and at that time I was an undergraduate student. So we have used this idea to transform this OAT into TAT. We start from this Hamiltonian, so this is standard OAT, and we can apply pulses. Rotational pulses is proportional to G1. It means, for example, in atoms, it's like applying a radio frequency field. And after doing some calculations, you can find the effective interaction is just this TAT. So using this method, we can break through the existing squeezing limit and approach the Heisenberg limited precision. So this black curve is OAT result, and this red curve is the result using our method. We can find it's better than the original result, and it can almost approach this Heisenberg limit. Then later we developed our method. For example, actually we can apply a series of pulses. So this kind of problem is just an optimization problem, as this year's Nobel Prize has mentioned that maybe the future of physics is AI. So about 5 years ago, we studied this kind of problem. We use the machine learning method. Here is a deep reinforcement learning method to optimize this pulse sequence. So based on this kind of method, we can find that we can use just a few pulses to reach almost the same performance. So this will greatly reduce the complexity. So I think it will be more friendly for the real experiments. Later, we want to extend this method to transfer the non-squeezing interactions into squeezing. For example, if we have this kind of interaction model, it corresponds to two subsystems. One is S and the other is J. For example, it can be obtained in this light atom interaction system, and also this kind of atom-atom interaction by for example, dipole-dipole interaction. So this kind of interaction originally does not have squeezing performance, but if we apply this kind of control sequences here, you can find that the effective interaction can also be this OAT case. So using this method, we can transform this non-squeezing interaction into squeezing interaction. So this is a picture of the evolution of states. So there are two subsystems, S and J. We apply pulses for this J subsystem, and we can find that for the S subsystem, the state evolves from this coherent spin state into a squeezed spin state. So we can look at this squeezing parameter without the rotational pulses. It's a black dashed curve as no squeezing. But after applying these pulses, we can obtain the squeezing. And we can compare the results with the standard OAT, and we can find that they agree with each other quite well. And we can also use more complicated sequences to realize TAT squeezing. Then we can get a better performance approaching the Heisenberg limit. And we also explore another kind of method without pulse. We just use continuous driving. So we study this kind of interaction. We add constant and continuous field here. So it is different from the previous results with pulses, because for pulses it has requirements for the experiments. Because applying pulses may induce some errors. But for constant and continuous field, the errors may be smaller. And for this kind of case, we use this so-called FN transformation. So this kind of transformation is usually used in condensed matter physics. For example, when studying superconducting, the formation of Cooper pair, because the electron interacts with the phonons of the lattice, and then there will be an effective interaction between two electrons. So in our case, the situation is similar, because the atoms in the subsystem S will interact with the subsystem J. Then there will be an effective interaction between the atoms inside the S subsystem. So we can obtain this effective OAT interaction. And then we can realize both OAT, also this TAT spin squeezing, and approach the Heisenberg limit. Then we further develop this method to generate other kinds of quantum states. For example, a GHZ state. If we consider the precision for the measurement, we can find that quantum spatial information plays a very important role. It determines the quantum Cramer law bound. If we calculate quantum spatial information for different quantum states, we can find that for coherent spin state, the quantum spatial information is equal to n, the particle number. And for this squeezed spin state, it typically is larger than n, but smaller than n squared. Then for the perfect GHZ state, we can find the spatial information is equal to n squared. So it means that actually the GHZ state actually has better potential than even the squeezed spin state. So for this GHZ state, when we plot this state on the Bloch scale, it means that half of the state is on the north pole, and half of the part is on the south pole. It is a superposition of these two states. The difficulty is that here the particle number n is quite large. As we know, actually, for just a few photons or atoms, we can prepare this GHZ state. But when we have a lot of atoms, it will be very difficult. There are some schemes using quantum gates to generate GHZ state, but just limited to several tens of qubits. Here we consider a lot of numbers. Then we come up with model. We call it a collateral spin XYZ model. So the Hamiltonian is like this. It's proportional to Gx, Gy, Gz plus its Hermian conjugate. So if we look at this kind of interaction, we can find that it is a three-body interaction because there are three operators multiplied together. So it means for the interaction, there are three atoms collision to each other, like this. So it's different from previous kind of two-body interactions. If we look at this model, we can first calculate its classical trajectory. We can find there are two large circles on the sphere. These large circles will benefit for the generation of the Z state. So we compute the quantum evolution of the state. We can find, starting from this coherent state, we can finally obtain this kind of separation on the Lorentz sphere. So for this separation, we can find that almost one half is on this pole, and the other half is on the back. So it's quite similar to the GSA, but slightly different. So we call it a GSA-like state. So we can calculate the time required to generate this kind of GSA-like state. The result is proportional to log n over n. So it means that if n is very large, this time can be small. This is very good for generation of this kind of state. How to realize this kind of collateral spin XYZ model? So we can develop our previously stated method. So just using a series of control passes. It's like this. After some calculations, we can find the effective Hamiltonian is just this collateral spin XYZ model. In this case, we actually need to cancel this second order terms and leave only this largest three order terms. So by starting from this original OAT model, we can use this kind of pulses to realize this effective XYZ model, and then realize the generation of GSA-like state. So we can calculate the quantum visual information. We can find that for the standard OAT is green curve, the quantum visual information is not quite high. But for our XYZ model, blue curve, you can reach a very high value. And the red curve is our method starting from OAT and using this rotational pulses. We can find the green, the red and the blue curve agrees with each other, and it means that our rotational pulse method is useful. And if we look at longer time scales, we can find that for a very long time scale, the green curve can also reach a relatively high quantum visual information. Because for the OAT model, it can also generate the GSA state, but it requires a very long time. So the required time is pi over 2. And in our case, the time is log n over n. It means that when n is very large, the time is greatly reduced. So reducing time means that we can overcome the decoherence. And we can compare the results for the measurement of precision. For a perfect GSA state, we can measure the parity. It means the odd or even number of atoms. And we can obtain the Heisenberg limit. So for our GSA-like state, we can also measure the parity. So this is a comparison of our results and the perfect GSA state. We can find for theta, theta is a parameter to be measured. For theta equal to 0, near 0, the results are almost the same. It means that our GZ-like state, although not perfectly the standard GZ state, can almost reach this Heisenberg limit. It has almost the same performance with the perfect GZ state. And compared with the perfect GZ state, actually our state has an advantage. That is, it's more robust to losses. When we consider the standard perfect GZ state, we can find it is actually very fragile for the particle loss. When it loses one particle, it will be a mixed state with no entanglement. So the quantum visual information will suddenly drop to the standard quantum limit for the for even one particle loss. But for our state, we can find that even multiple atoms are lost. The quantum visual information can still keep quite high. So the reason is that actually for our case, if we expand the state in a decade space, we can find that it has a wider distribution, so it will be more robust to the particle losses. Okay, this is the first part, and then I will turn to the second part. So we want to use this kind of quantum state to do the precision measurement. So we are focusing on the measurement of magnetic field. But at present, we need to construct the experimental system and also need to remove the classical noise. So at present, we haven't realized the quantum state enhanced measurement yet. So we think up of other kind of methods to improve the measurement precision. As we know, actually, for the magnetic field measurement, there are a lot of applications. For example, search for dark matter, search for exotic force, and for space exploration, and also for the measurement of the magnetic field of brain. So we have work for excitation point enhanced magnetic field sensing. So this is the basic experimental setup in our lab. So in this experiment, we make use of non-Hermitian properties of the system. So originally, actually, for the sub-Zeeman levels, we can find the dissipations or the relaxation rates are almost the same. But we can selectively couple one of the state to the excited state. And in this case, one of the states, this is state 1, will have a larger relaxation rate. And in the subspace of 0, 1, 2, we can find they form a non-Hermitian system. And for this non-Hermitian system, we can observe the so-called excitation point. We can realize the signal enhancement because of the excitation point. And then we can explore the PT symmetric, the PT is the parity time, PT symmetric line width narrowing. Because in our measurement, actually the line width is very important because narrow line width means better precision. Then in our case, we use a method to measure the conjecture of this collective spin, and then do the feedback, and then obtain a effective parity time symmetric system, and then obtain this line width narrowing effect. And we can use our magnetometer to search for the so-called fifth force. According to the standard model, there are only 4 fundamental forces of nature, but the new evidence of experiments have suggested that there may be other exotic forces beyond the standard model. Then how to determine whether these forces exist? Then we need this precision methods. So we use our atomic magnetometer to search for the fifth force. So actually, if there is this spin-dependent exotic force, then it will generate an effective magnetic field. So our sensors, these atomic spins, can obtain this field, and then there will be measurement results. At present, we haven't found any evidence for this kind of exotic force, but we set new bounds for the coupling coefficients. So the bounds is much better than the previous experimental results. And we also developed another kind of magnetometer using this kind of cavity optomechanical systems. So this is the experimental design, and the basic principle is that we use the magnetostrictive effect of the material. So this is a sketch of our device. So use this magnetostrictive material, we can transform the magnetic field into the displacement. And we here use optical resonance because we have a high refractive mirror here. And also we use the mechanical resonance and to enhance the signal. In our lab, we can measure measurement sensitivity of magnetic field of 620 femtopascal per square root hertz. So this is quite a good sensitivity, and at the same time, the advantage of this device is that it can work under Earth's magnetic field, and it can operate at room temperature. So, okay, this is the summary outlook. So we have studied the quantum state propagation based on interaction control, and we have studied the high sensitivity magnetic field measurement. So in the future, we want to surpass the standard quantum limit using quantum state. So thank you very much.
Okay, good. So is there any question or comment from the talk? Okay, so I have one question about your fifth course. Is there any motivation? I mean, if there's any phenomena you cannot explain using 4 courses, then probably there will be one motivation.
Yeah.
Or is there any other is there any phenomena you want to explain?
Yeah, actually, so for this kind of motivation, there are other kinds of experimental results. For example, in high energy physics, they have results suggesting that the standard model is not perfect. And some theorists have some idea that there might be so-called exotic force. So for different kind of theory, there are different expressions for the Gibbs force. But here we are searching for this so-called spin-dependent exotic force. It means that this force depends on spin, but it is not an electromagnetic force. So if we can discover that, it means maybe there's the so-called Gibbs force. But also, I want to mention that this is difficult to realize experimentally. So what we can do here is set a limit for this force. So if this force exists, then the coupling coefficient is lower than this number. Then we can do this. So I'm not sure whether we can measure it finally, but we are continuously working on this. Because when we improve the measurement sensitivity, we can measure the results maybe we never see before.
I see. So basically you want to find something which is not spin-spin interaction, spin-orbit interaction.
Yeah.
So something which is not known.
Yeah, not known.
Oh,
yeah.
Okay. Okay. Good. Thank you very much. Oh, yeah. One more question.
Yeah, it's not my question. It's a question from online. So I read the question. In the first part of the talk, how is the parity in the number of atoms measured experimentally?
Yeah, this one. So this parity is like this. It's the back of all the matrix. So actually, for different systems, the measurement method may be different. Actually, the most simple method is to just count the number of atoms. For example, in ion trap system, you can imagine every individual atoms, and you can see which state these actually ions, these ions are, and then you can obtain this parity of the system. Yeah, and in other systems, there are other kind of method, especially for our mentioned systems. For example, the collective spin, which cannot be individually addressed for each atom, which cannot be individually addressed. Then actually we have ideas about how to measure this parity. The idea is that you need to also do some dynamic control and finally turn this parity into other quantities. Yeah.
Okay, thank you.
Okay, so if there's no question, then the president of AAPP is Professor Chen. We'll close the session.
Okay, so I have two announcements. First one is for the online participants, and the second one is those in this room. Okay, so first announcement for the online participants. So we'll close the Wednesday session of the Asia-Pacific Physics Week 2024, and we'll continue the Thursday session tomorrow at 2 p.m. in Seoul time by the exciting talk of the Shinhwa Peng about the measurement of the extremely weak magnetic fields. Okay, and then so thank you very much for the online participants. And then for those in this room, we'll have a group photo. Okay, thank you.
Okay, so please come to the front to have a group photo.
Because the place is very
After this is a free time.
Oh, yeah?
Yeah, you can go on.
Dinner still at 6.
You can check the
There.
Yeah, there is no problem. There is no problem.
For the session, yes. The rest of the time is for simply networking.
Binigyan daw ng grade dalawa. Pinapigil yung talagang kulang.
Ang dulong ko.
Predict niya yung 2020.
Reggie, lakad, ay, free ka ba? Lakad tayo. 6 pa ang dinner. Lakad tayo.
Kuha ko ng dyan.
Oo, mag-akit lang din ng gamit. Meet na lang tayo ng lunch. Okay.
Now I ask
For real. For real. For real.
Thank you so much.
아마 저희가 그때 요청 드렸잖아요. 원래가 되지 않았지만 아침마 다시 요구를 했어요. 전 식사 끝나고는 옮겨주시면 좋을 것 같아요. 아니면 내일 아침 9시 전에 네.
Thank you.
카메라가 뭔가 그래.